Hi, everybody. You know who I am now and what I'm talking about. This work is a collaboration between folks at UCLA, UMass Amherst, let me take this off, and UCSD. Oh. So software has bugs, and these bugs can range from the relatively benign to the catastrophic. And in 2003, the National Institute of Standards and Technology estimated that software bugs were costing the economy $60 billion annually. And that was in 2003, when software was a much smaller part of the economy. So like now, you can only imagine how much software bugs are costing us. There are many different techniques for finding bugs and preventing them. People use testing, model checking. But the one I'm going to talk about today that I'm very excited about is foundational verification, where we write a mathematical proof of correctness about our program. Now, I'm excited about foundational verification because it's been shown empirically to be able to produce bug-free programs. And it's been used in all sorts of applications, like compilers, web browsers, even operating system kernels. And what do I mean by empirically produce bug-free programs? Well, in 2011, there was this project CSmith that tested a bunch of compilers. It had a new technique for fuzzing compilers. And they tested the Concert verified compiler as well as two industry standard open source compilers. And what they found was that Concert was the only one where they couldn't find any wrong code errors in the code base and no problems at all in the verified portion of Concert. So this is really impressive. We've actually managed to produce a piece of software that is completely bug-free. So why don't we just do this all the time? Why aren't we constantly foundationally verifying everything? Well, turns out foundational verification is really hard. It takes a lot of expert labor to get anything done. Concert took about 3 person-years to verify, and Cell4, a verified operating system kernel, took 22 person-years. Now, this may not seem like a lot on the scale of industrial software development, but keep in mind, these aren't like 3 normal person-years. This is 3 like PhD-level person-years. And these software artifacts are orders of magnitude, like hundreds of thousand times smaller in terms of lines of code than their industrial counterparts. So how do we usually deal with hard things that take too much labor as programmers? Well, we try and automate them. If we can automate some or all of, or most of foundational verification, then we can produce more bug-free programs and have fewer bugs in software we rely on. So let's take a step back and talk about how foundational verification works. You start with a program and some sort of description of how that program is supposed to work, a specification, and you give it to a really smart programmer who then produces a theorem and a proof of that theorem to send to a proof checker. But this isn't the whole story, because it's not just one proof. It turns out that proofs, like any software project, need decomposition. You wouldn't write a database as like one big function, and so you don't actually write your verified software as just one proof. You write it as many. So you decompose the theorem that you care about into multiple helper lemmas that allow you to actually prove the thing you want. So helper lemmas are really common. This verified compiler Concert can be thought of as only really having one top-level correctness theorem. There's a meaning of the input language, a meaning of the output language, and the correctness theorem is just that programs translated between have the same meaning in the end. But there's thousands and thousands of other theorems and lemmas in Concert that are proven to allow us to prove this one top-level correctness theorem. And unlike when you're writing proofs, there's no built-in automation in the tools we use for decomposing proofs. So if I have a proof goal of a particular form, I might be able to run a proof search tactic on it. But there's nothing in these tools that'll say, you know, I'm trying to prove this one thing, give me the other things I need to prove first. So our goal with this work is to be able to automatically create helper lemmas from the theorem that the user is trying to prove so that they can more easily verify software. And this is called lemma synthesis. The lemma synthesis is actually a really hard problem that people have been studying for a long time. Like a lot of things in proofs, in general, it's undecidable. But by restricting the domain, we can make progress on it. So for this work, we're going to be talking about lemma synthesis for equality goals, when you're trying to prove two things are equal, that don't have any extra preconditions added on. And this is also the scope of most of the prior work we'll be talking about. So prior work in lemma synthesis falls into approximately two camps. There's term rewriting works like isoplanar and rippling, where you take the user's goal and you rewrite it with some basic rewrite rules. And there's enumeration-based synthesis, like QuickSpec and HipSpec, where you start building lemmas from the ground up and try and find valid ones. Now, term rewriting is really nice because it's goal-directed. It's trying to produce lemmas for the thing you're trying to prove. But it can have limited expressiveness because it has to work within the structure of the goal that you have. On the other hand, enumeration-based synthesis can be really, really expressive, but it's not goal-directed. So you'll produce a lot of lemmas, but they won't necessarily be the ones you care about right now. Now, the most common of these prior approaches is just generalization of your goal. And in the benchmarks we're going to be looking at, that can get you about 20% of the lemmas you care about. So that's okay, but we can do better. So our new approach is a data and sketch-driven lemma synthesis tool for Coq that's both goal-directed and expressive, called lfind. It takes the user's theorem and partial proof, written in Coq, and produces a list of candidate helper lemmas. And our approach is a 65% success rate on our benchmarks. And that's by a conservative success metric, so it could actually be a little bit more. So let's walk through a simple example to let you know what I mean and how this process works. So let's say we're trying to prove this lemma about lists, that for all lists, if you reverse a list twice, you get back the original list. It's pretty simple, right? So the user will put this in their theorem prover. They'll write down what they're trying to prove, and they'll start to prove it, dispatch some cases, do some induction. But at some point, they get stuck here. And that's because this theorem isn't inductive. So when you get to this point in the theorem, or in the proof, your inductive hypothesis is not of the same structure as the thing you're trying to prove. So because they're stuck, they can run lfind, and we'll take their current goal that they're trying to prove, and we'll derive a helper lemma for them. In this case, rev append, which is saying that if you reverse the append of two lists, it's the same as appending or reversing each list and then appending them in the other order. And this actually is an inductive goal. It can be proven directly, and then it'll allow you to prove the thing that you care about. So how do we go from this stuck state that the user is at to this target lemma? There's a few challenges we have here. The first is that the target lemma might have new variables that weren't present in the original goal and don't correspond to anything from that goal. It might have, it has to be expressive, right? Because it might be of a different structure than the original goal. The target lemma needs to be logically consistent and actually meaningful. And it has to be useful. It has to allow the user to prove what they want to prove. So we've taken these four challenges, and we built a system with 4 parts, one for each. We start with the user's stuck goal. We generalize it. We synthesize a subterm. We filter out invalid lemmas, and then we rank the remainder. So our first challenge is we need new variables, right? And so what we do is we pick some parts of that stuck goal to replace with fresh variables. And this gives us a generalized goal. Now, this can often make goals inductive on its own. But like we said before, generalization by itself only gets you about 20% of the lemmas you care about. And you can see why right here, because we're trying to relate these variables y and z to these other variables a and x, which have no a priori relation. So this isn't actually a valid lemma. So to fix that, we're going to move on to our next challenge, expressiveness, where we're going to also pick a part of this goal to replace with a whole. Now we have a lemma template that reverse of y append to z equals something, and we need to figure out how to fill this hole. So if we just do this using a numerator-based synthesis, we can get about 46% of the lemmas we care about. But that's still not quite the 65% that we get in the end. So what we do instead is a data-driven approach where we use an example-based program synthesizer to fill this hole. But this brings to mind like 2 challenges, right? How do we determine the example outputs that we're going to give the example-based program synthesizer? And how do we make the examples overall goal-driven? And the answer to both is kind of the same, which is that we're going to try and mimic the behavior of the original stuck state. So we'll start with that original stuck state and generate some examples for the variables that were in that original goal. And then we'll use our generalization map to generate variables or values for the new variables. And similarly, we can use the expression we replaced the whole with to generate output examples. And now with these input and output examples, we can pass them to an example-based synthesizer and get a new expression to fill the hole. Now that we have our lemma template and our hole filling expression, we can add them together and get our candidate lemma. You might have noticed that up to this point, we've been making a lot of sort of arbitrary choices about which expressions to generalize and where to put the hole. So we actually have a lot of candidate lemmas at this point. We made every single possible choice. And this is too many to present to the user and find useful. So next we need to filter that down. And that runs into our third challenge, logical consistency, which is that the lemma needs to actually be valid. So we can take lemmas that we have and throw them at a property-based tester, which will just create a bunch of examples and try and run them through that and see if those lemmas are valid. Of course, this isn't going to work for all the higher order lemmas you could possibly care about, but for proving things about programs, this is generally okay. And this approach can eliminate about a third of the lemmas we get through our prior phases, but that's not enough. We still have too many. And a big reason that is because we may have taken a lot of different paths that end up in approximately the same place and ended up with lemmas that mean basically the same thing, but maybe written a little different. So we have some equivalent expressions or we rename the variables. But we can actually use Cox's unification algorithm to eliminate some of these. And you can see the paper for how we do this specifically. We have a little bit of a clever trick here. And this eliminates 85% of the remaining lemmas. So now we've eliminated over 90% of the lemmas that we started out with, and we actually have a reasonable number that we can present to a user. So our final challenge is that the lemmas have to be useful, right? We need to make sure that these lemmas are going to be provable, that they're going to prove the goal. And that's our ideal. So we want the user to be able to prove the lemma, and we want them to be able to take the lemma and prove their goal. And to figure this out automatically, we use a proof search tool to try and prove the lemma and prove the goal. And if they both succeed, if we're able to do that, we're going to call this a category 1 lemma. If we can use the lemma to prove the goal, but we can't necessarily prove the lemma right yet, then we're going to call this category 2. And otherwise, we're going to call it category 3. And by using these categories, we can produce a total ordering on the lemmas that we have at this point. And within each category, we just order them by size. So that's our approach to data-driven lemma synthesis. We take a stuck goal, we generalize it, we synthesize, we filter, and we rank. So now we'd like to know how well does this actually work. So we decided to run on some benchmarks. They sort of fall into two different camps. There's existing Coq projects, things people have formalized, including an expression compiler from CPDT and a full adder circuit that was formalized in this Coq contribs project. And we also have some benchmarks from prior work, prior papers on interactive theorem proving and lemma synthesis. And what we did was, for each theorem in one of these benchmarks, there are some places where they would try and use some external lemma, right? And maybe that was defined before, but maybe they needed to generate it from scratch. We don't know, because it's external. And so we take each of these places and create a new version of that theorem where they run up to that lemma, and then they run lfind. And because the theorem might have multiple helper lemmas it uses, each one can have multiple benchmark locations. So in total, we get 232 test locations for our tool. And we want to know if we actually succeeded when we produce these lemmas. So if we are able to produce a lemma that allows a fully automated proof, we know that's a success. We know that we made a lemma that allows you to prove your goal. And even if we didn't, because maybe you still need another lemma, or maybe our prover just isn't powerful enough, if the lemma we generate matches the human written one that we found in our original benchmark, then we consider that a success. And all other lemmas, we're going to consider failures. Now, this is not going to count every single useful lemma as correct, because it might be that there's multiple lemmas you can use at a point, and neither of them gives you an automated proof, but one of them the human chose and we found the other. But every lemma that we count as correct is going to be useful. So that's what I meant by a conservative metric. We have some black box components we use during our tool. So for our proof generator, we use proof about 9001. For our example-based synthesizer, we use the myth synthesizer. And for our property-based tester, we use quick check. And what we found, like I teased at the beginning, is that 65% of the time, we can find the correct lemma in the top 10. Yeah, it says top 10 behind that window. And 62% of the time, we can actually find the correct lemma in the top 5. And even if the top 5 isn't good enough for you, 56% of the time, the first lemma we give you is the correct one. So 56% of the time, you can just call our tool, and we give you the correct lemma right away. Now, this doesn't, oh, yeah. So you might think this is just running on sort of like trivial examples, so I wanted to show a few of the lemmas that we actually generate. For that expression compiler I was talking about, there's a correctness theorem about compiling an expression and then executing the instructions as the same as evaluating the expression in an interpreter. And we're able to generate this more general version of the goal that also includes non-nil stacks and extra instructions at the end that allows us to be inductive. For a full adder circuit, there's this proof of adding one number to another, where one of the cases is more complicated and you sort of have to derive it as a separate lemma, and we're able to derive that lemma. So this doesn't run right away, unfortunately. The average runtime for generating all the lemmas in our list is about 5 minutes. But if we're able to find a category 1 lemma where we know that it could automatically prove the thing, we can stop right there. That only takes a little bit over a minute. Not quite fast enough for interactive use yet, but there's a lot of opportunity for optimization and parallelization in our approach. So we think that someday it can happen just right in your IDE as soon as you need it to. So I mentioned some related work a little bit back. I'm going to go over that a little bit more. Isoplanar and this automation ACL2 do just generalization only for finding helper lemmas. There's these Rippling and Xeno projects that do generalization plus some goal-directed rewrite rules. QuickSpec and HipSpec, again, do enumeration-based synthesis. And ADT is the most similar because it does generalization and sketch-based enumeration. So this might seem like very similar to our work, but again, it's only enumeration. It's not data-driven synthesis for your sketches. And the sketches are actually provided by the user. They're not derived from the goal. So in the future, we'd like to overcome some of the limitations of our scope. We want to support relations other than equality. And we want to be able to use the hypotheses in your stuck proof context to generate lemmas that have preconditions. We also want to be able to rank the lemmas better using machine learning. So the right one is more likely to be in the top 10 or 5. And eventually, we'd like to integrate this lemma synthesis back into a proof search tool so that it can be looking for a proof, get stuck somewhere, generate a lemma, prove that, all without any user interaction. And finally, if we improve the black box components that we're using, our approach can have a higher success rate. So that's my work on data-driven lemma synthesis, where we start with a stuck goal, we generalize, synthesize, filter, and rank to 65% of the time, give the user a correct lemma that they can use in their proof. Thanks.
Thanks. Questions? Yes, Ilya.
Thank you so much. Thank you, very nice work. I have at least 2 questions. So the first one, okay, could you go back to your reverse lemma example, the list reverse?
Yeah, it'll take a little while though.
Yeah, okay, maybe this one will do, yeah.
Yeah.
Okay, so I'm kind of surprised that you didn't mention a technique that seems very relevant, and this is cyclic proofs, known as induction-less induction. And the idea is that when you have something like your initial goal that is not inductive, and you start trying to prove it, and you go down the line of your derivation, and you notice the same goal has appeared twice, higher and lower in the derivation, then you can just imagine that this is probably an inductive statement that you might want to abuse as a lemma. And people used it a lot in verification of looping programs and even in program synthesis.
Yeah.
Okay, question. Did you consider that, or this is just orthogonal to what you're doing?
I think we didn't really think too much about that. I think in this case, you don't actually see the same goal twice when you're trying to prove this lemma, at least when I tried to prove it. So it wouldn't always apply in all the cases where we apply.
Okay, well, okay, fine, because you don't try to go deep enough into the proof derivation, I guess, because to see it twice. Okay, and I have a second question. So this is all about like proofs about pure programs in Galena. And in my impression, there are quite, okay, so the way Calc is very widely used nowadays is not by proving things about programs in Galena, but by proving facts about programs in domain-specific logics, such as separation logic. And that also is something that might require helper lemmas. So I understand that this is not something that you address, but would it be possible to extend your approach to discover lemmas for embedded domain-specific logics into Calc?
Yeah, I think as long as we could get the synthesizer to synthesize terms and quick check to synthesize examples, we wouldn't have any trouble with that.
So my question is, how do you use this tool? What is the workflow of using this tool?
Yeah, so it's actually implemented as a tactic. It kind of gives you like output in the feedback buffer. See if I can click back far enough here. But you can use it like while proving your thing. You just kind of call the lfind tactic and it says, here's some lemmas, and then you copy those out somewhere else and try and prove them.
So I have a question about the evaluation you did. So just to make sure I understood the evaluation correctly first. So you took theorems that were already proven, and then for some of the things that were used in the theorems, you then removed them and had it synthesized instead.
Yeah.
Do you think it's possible that it performed a bit better because the proof structure was already quite well written because it was proven before? Like in practice, I might be going off in the wrong direction, so it might not. It might not be as easy to find a lemma that's actually going to be easy to prove what I'm trying to do.
Yeah, so I guess deriving the lemma, or even getting to the stuck state where you can derive the lemma, requires that you already sort of know what you're doing in the proof. Mm-hmm. I guess there's other work on automatically trying to figure out how to get to that point in the proof. We're just worried about like once you're stuck, we'll give you the best options where you are.
Okay, so I guess just to make sure I understood, so it's kind of assuming I have the entire proof written and there's just one block in the middle I'm not sure about, so kind of like, I guess comparable to like sketch programming then as opposed to...
No, you don't need the entire proof. You only need the proof up to that lemma, so nothing after.
I guess more what I'm thinking is maybe I'm writing a proof then and I'm actually going off in the wrong direction without realizing it. So like here we know we're going in the right direction because the proofs actually exist. So I'm wondering how that might affect the synthesis results.
Yeah, I mean, if you're at a place where no helper lemma is going to help you, there's nothing we can give you. But ideally, we'll get other tools that can kind of make sure you don't get to that place.
Okay, that makes sense. Thanks.
Other questions?
The other side.
Do you see opportunities for lfind to use lfind?
Well, yeah, I guess like we have this problem always where if you need two helper lemmas, right, then trying to find the first one is really hard because you won't be able to tell that it was the right thing to complete the proof because you still need another one. So we definitely have thought about kind of like recursively calling lfind then. Right now, with the performance we have, it just blows up a little bit too much. Because by that point, you've already generated a bunch of candidates, and now you need to generate a bunch of candidates for each of your bunch of candidates. But I think that would like be the ultimate goal, is that it's sort of like lfind goes in the prover, then the prover goes back in lfind, and ultimately like it's generating a sequence of lemmas.
Other questions? Actually, I have one. Can you use this tool to kind of strengthen the induction hypothesis?
Yeah. So a lot of what this is doing is sort of like strengthening the inductive hypothesis, right? Like when you generalize, you're strengthening your inductive hypothesis. And then the synthesizing, like sometimes, isn't quite strengthening because it's not exactly that thing. But yeah. So often, like if generalization is all you need, then the first generalization pass will give you the red lemma and we'll spit it out right there. But yeah, I guess there's other forms of strengthening that we don't necessarily support because, figuring out what implies what is hard.
That's great. Do you have a concrete example somewhere during the experiment?
A complete example?
Did you have a concrete example of that?
Oh, of strengthening the inductive hypothesis? I don't think I have it here. Okay. There are definitely examples where all we need is generalization, and that's a strengthening.
Yeah. Thanks. Other questions? If not, let's thank the speaker again.